Okay, we started on, what did we start on last time? A representation of supersymmetry algebra with central charges. So, SUSY with central charges. And in particular, we started with a discussion of n equal to 2. N equal to 1, there are no central charges, so there is nothing to discuss. And the algebra is commutator of q alpha I with q beta j is root 2 times root 2 epsilon alpha beta epsilon I j, and we argued that there is only one real charge, and we called it Z, so mod Z. Phase of this is irrelevant because you can absorb it away. And for conjugate charges, q bar q beta bar j 2 root 2 epsilon alpha dot beta dot epsilon I j mod Z. Epsilon I j up is inverse of this. And then q alpha I q bar beta j is 2 sigma mu p mu alpha beta dot delta I j. So, massive multiplet, massive states means I can choose P mu to be M 0 0, the rest frame for every one of them. It's real. We argued that Z is real. That's why we put a mod here. Okay, we start with a complex number, but we said phase of Z is unimportant because phase can be, by rescaling Q's, I can absorb half of the phase here, half of the phase here, and I would have a Z bar here, which would have the inverse phase, and conjugates would take half of it here, half of it here. This relation will not see the phase. So, what happens in the rest frame, these two commutators stay as they are. And q alpha bar I q beta bar dot j but this one becomes simpler. Since only one component of P mu is there, M sigma 0 is alpha delta alpha beta, that's a unit matrix. and I takes values 1 and 2 because we are doing, and so does J, n equal to 2 supersymmetry. Next, what we said is that let's construct a linear combination of these 4 supersymmetric charges. 4, alpha takes values 1 and 2, I takes values 1 and 2, so there are 4 of them, and the conjugates. So let's make linear combinations of these, and linear combinations are, and we call them A alpha, 1 by square root 2, Q alpha, spinor index, and 1 is the I equal to 1, the internal space index, plus epsilon alpha beta dot. We have introduced now an epsilon symbol with an undotted and dotted index, and we will explicitly write what that is, maybe somewhere here. 1, 2 dot is same as minus 2 dot 1, and is same as minus 2, 1 dot, and that is minus 1. And epsilon 1, 1 dot is same as epsilon 2, 2 dot, and both are 0. So Q bar beta dot, and this was 1 here, the I equal to 1, so put I equal to, so let me put it down. I equal to 2. So it's for alpha equal to 1, this is 1 minus 2 dot. And another combination, we'll call it B alpha, the change of sign. Then take the conjugate of this, conjugate combination, and call it alpha dagger, A dagger alpha. Alpha dot Q bar alpha dot 1 plus alpha dot beta Q beta and 2. This is the internal space index, J equal to 2, I equal to 2. And other combination, we call that B dagger. You're right, Mr. Bart. It's the same combination with a minus sign changed, plus changed to minus. Alpha. P alpha transforms under A alpha transforms as half 0. I mean, this has been conjugated, so because of this, this will transform like. Now, the reason to do that is because if you do introduce these linear combinations of the supercharges, then the this algebra takes a simpler form. And what is that? And I thought, well, this would be an exercise that A alpha anti-commutator with A beta dagger is 2m plus root 2 mod z delta alpha beta. And B alpha, B beta dagger anti-commutator is 2m minus root 2 mod z delta beta. Notice the sign. One with plus and other one. And all other anti-commutators are 0. So what does this do? It breaks our algebra into product of two algebras, algebra of alpha A's and B's, which don't talk to each other because all the commutators are 0. So two independent algebras. And like I said, important thing is notice is that here on the right side you have a plus sign, you have a minus sign. That this minus sign has an immediate consequence. That is, m is always greater than or at best equal to root 2 mod z. So the mass of this representation is always bounded from below by the mod of z, the root 2 some normalization. And it's very easy to see it from here. Look at this algebra. So start, see for representations what do we start? We start with the vacuum of the algebra, omega, vacuum state. Start with a state on which B alpha is 0. And on such a state, let me apply this, B alpha dagger plus B alpha dagger B alpha, and take the expectation value for every value of alpha. For alpha, see they are repeated indices, but they are not summed. That's what it means, every value alpha. So take 1, 1, 1, 1. There are two such equations. The other equation would be 2, 2, 2, 2. For each of them, use this algebra. This one. It's 1, 1, so delta 1, 1 is 1. Or this other equation is 2, 2. So the same equation you will get. Now on the left hand side, because this is 0, all you have is this, and that is B alpha dagger omega expectation value is equal to 2m root 2 z. If you have normalized this to 1, that's 1. Otherwise, some positive number, because it's the mod of the state omega. Now, this is mod of this state B dagger on omega norm. So, therefore, this is positive. And this immediately implies that m has to be greater than root 2 mod z. particular value when m is equal to root mod z, when this equality holds, is a special case. This very nice properties. But when m is not equal to this, so m not equal to root 2z mod z, then representation theory for this algebra is same as that with no central charges. Is it clear? So, you can, the way we constructed the earlier representations, you can do that, start with a vacuum state and apply A oscillators and B oscillators on them and construct the representation. That is exactly the same as one without central charges. But when m is equal to root 2z, the representation changes. And when m is root z, there is a name given to these states. These are called Bogomolny. How do I spell it? I always have a problem. Bogomolny. Sometimes they are called Bogomolny states, sometimes they are called Bogomolny Prasad Sommerfeld states, or BPS states. That is a name given to these states. The names that saturate this mass and central charge relation. Yes. Yeah. Not the same masses. For every yes. No, that's not right. What you do is that you normalize. See, because this is what you can do is you normalize these by this and construct those oscillators. Because you see, p square is still m square for all of them. Okay. So, BPS states. Now, what happens in BPS states? And BPS states, right hand side of this second anticommutator is 0. So, the B oscillators completely decouple from the theory, because all their commutators are 0. BB is 0, B dagger B is 0, BV with A's is 0. Okay. So, which means I can take all of them acting on state 0, both B and B dagger. So, therefore, we are left with only this algebra. So, for such states, such a representation, we are left with only A alpha dagger, A alpha and A alpha dagger algebra. And to put it in a way where we can easily read off the representations, we scale these oscillators A alphas, define A alpha hat to be A alpha divided by root 4m. And A alpha dagger hat as A alpha dagger by root 4m. When they are equal, this is equal to 2m times 2 is 4m. So, the scales out. Then the algebra takes the form A alpha hat A beta hat commutator is 0 and A alpha and A beta anti-commutator or A beta dagger anti-commutator is delta alpha beta hat. And now remember, alpha takes values 1 and 2, so does beta. So, this is the algebra of two fermionic oscillators, alpha 1 and 2, and their daggers. So, we do the same trick, start with vacuum in inverted commas, vacuum state, define where A alphas on that vacuum are 0, and construct the states by applying A alpha dagger on A hat alpha dagger. So, let me write a table for the states now. Start with the state. Degeneracy, number of states, Jz spin, and whether bosonic or fermionic. Now, there is one more piece of information. Remember, from what we had done earlier, we have realized that Q alpha 1 Q alpha equal to 1 raises the Z spin by half unit, and Q 1 dot 2 this is not 1, this is 1, this is 2 dot, and Q bar dot also raises. On the other hand, if I take alpha equal to 2, then Q2 lowers the Z spin by half unit, and this is 2, therefore, this is 1 dot, Q1 dot lowers the spin. That means A alpha, A1 dagger raises Jz spin by half unit, and A2 dagger lowers Jz spin by half unit. So, let me start with the vacuum state, ground state with one state, and let us give us Jz spin value to it. Now, if Jz is integer valued, it will be a boson, and if Jz is half integer value, it will be a fermion. And now apply A dagger alpha on that. So A alpha takes two values, it's 1 and 2. So there are two such states here. A1 increases the J spin by half unit and A2 lowers the spin by half units. So I have two states, one with J plus half, other with Jz minus half. And if this was a boson, this would become a fermion, and if this was a fermion, this would become a boson. Now, let me, sorry, this was dagger, right? Act two of them. Because daggers created. So two of them. Two of them, alpha takes values 1 and 2. They cannot take the same value 1, 1 because that is the same fermionic oscillator square and that is 0. So it can take 1 and 2 and 2 or 1. So there is only one state. And one of them is with index 1, other one is index 2. With the index 1, it increases the J spin by half unit. Index 2 decreases the J spin by half unit. So result net is Jz. And if this is a fermion, this would be a boson and fermion. So total number of states is 2 bosonic and 2 fermionic. Which is 4. In particular, let me take a special values for this one. So put Jz equal to 0. So Jz equal to 0. Then this would be half plus half minus half. This would be 0. So this multiplet is made up of a scalar, and 2 fermions with Jz value plus half and minus half. That makes one Majorana fermion. So it's made up of 2 scalars. So let me put it. Minimum Jz value or vacuum Jz value. Vacuum Jz value Q. It has 2 scalars. In fact, there is one scalar and one pseudo scalar. And one Majorana fermion with Jz values plus minus half. It has to be a Majorana fermion The reason is it cannot be a Dirac fermion. Why it can't be a Dirac fermion? Because massive Dirac fermion has 4 independent states, but this one has only 2. So it can be only a Majoranov fermion, and Majoranov fermions can be massive. So, and all of these would have the same mass m. Right? Now let me take another example. Jz value, what have I taken? Half. So half, and then one of them will increase it, another one will decrease it by half unit. So I'll have 2 states with Jz value 1 and 0, and this would be still half. Okay. So in this state, I have 2 bosons, but one of spin 1, another spin 0. Jz spin 1, Jz spin 0, and I have 2 fermions with same spin. That does not make a representation of the Lorentz group. Right? But now, if I take another state with Jz, lowest Jz minus half, then one of the oscillators will increase the helicity by half, make it 0, other one will reduce, make it 1, and these together can make a CPT conjugate, or a massive representation of the Lorentz group. Is that clear? Now this object here is the one with vacuum Jz plus minus half. Is a reducible representation of SUSY, made up of 2 representations of SUSY, one with the vacuum Jz plus half, one with the minus half. And then it has, what is the content it has? It has Jz 2 values and Jz plus 1 and minus 1. Spin 1 object has Jz values plus 1, minus 1, and also 0. So one combination of these zeros will give me the Jz equal to 1. Give me the spin 1 component. The other one will be a real scalar. So this is a theory of a real scalar plus one vector, massive vector. So this has 1 degree of one state. One vector has 3 components. Spin 1 vector is spin 1. So it has 3 components plus Jz values plus half, minus half, plus half, minus half. That gives me 2 Majoranov fermions, and 2 Majoranov fermions are equivalent to 1 Dirac fermion. Now, this multiplet has 4 component. This multiplet, this is a massive multiplet. Multiplet of n equal to 2 SUSY. But this is a BPS massive multiplet because it saturates the BPS state. Has 4 components, 4 states. Each one of them has 4 states. And we give this a name, call it short multiplet. Why short? We'll see it in a moment. As compared to n equal to 2 massive multiplet without central charges, which has dimension 2 to the n, 2 to the 2n, that is n equal to 2 is the 16, 16, 2 to the 4, that's 16. So, the massive multiplet without central charges has 16 components. Massive multiplet of BPS saturated multiplet has only 4 states. So, this we will call long multiplet. That is the reason for long and short. So, that is one fact. There is another nice property. What would be the number of states of n equal to 2 massless multiplet? The dimension or number of states of n equal to 2, or number of n equal to 2 states, n equal to 2 massless states in a multiplet, in a super multiplet. From now, what do we learn from last time? Can anybody remind me? This is 4. This is exactly the same number as the number of BPS saturated states. So, this is a short multiplet. This property is a very nice property and important property, that the dimensionality of a massless supermultiplet of n equal to 2 and a massive BPS multiplet is the same. N equal to 2, we are doing it right now. Same true higher also, we will go to that. It's a very general property and there is a basic reason for that property, we will see that soon. But they do not have the same mass. One is massless, other is mass. Okay. And there is another interesting property. This is also equal to number of states of n equal to 1 massive multiplet. Because that massive multiplet will have 2 to the 2n, and n is 1, for that is 4. So, remember these properties, we will come back to this property, particularly this one and this one, that they have the same number. So, let me now go to n equal to 4. So, n equal to 4, Susie, we have 6 central charges now here. This is with central charges. So, we have Zij. I takes values 1 to 4, Z takes values 1 to 4. So, which means we have 6 of them, 6 central charges. 6 complex numbers, 1 2, 1 3, 1 4, 2 3, 2 4, and 3 4, 1 2 3 4 5 6. Each one of them is complex. Zij's are 4 cross 4 antisymmetric matrices. There is an elementary property that by a U4 rotation, I can always rotate a 4 cos 4 matrix, antisymmetric matrix, into a form. So, Zij goes to Zi prime, Ij, Ul, Uj, k, Zl, k, where this has a form 0, 2 cross 2, 0 block, a 2 cross 2 matrix called a D, minus D, where D is a diagonal 2 cross 2 matrix with non-negative eigenvalues, and let us call them Z, small z1 and z2. This is always possible. So, if I take the n equal to 4 supersymmetric algebra and do a U4 rotation on it, Q's will also change accordingly. I will have a new algebra for Q primes, for which the central charges will have this form. So, though I started with 6 complex charges, really there are only 2 real central charges in this theory. The more generalized argument, like we had in n equal to 2 case, where phase rotation did it for us. Here phase rotation is U1 transformation or O2 transformation. Here it's a U4, sorry, U4 transformation. And then we just take a linear combination of the Q and Q bar generators, like we did for n equal to 2. I will not do that algebra, and construct the A oscillators and the B oscillators. We'll have 2 of A oscillators and 2 of B oscillators. Like, earlier we had only 1 A oscillator and their conjugate. Now we will have 2 A oscillators and 2 B oscillators, each carrying an index alpha. And if you look at the algebra of theirs and work it out the way we said it, that there is a mass bound for n equal to 2, there is a mass bound also here. That mass is always greater than or equal to root 2 times the small z1 or small z2. And like I said, let me write it again, Qi and Q bar alpha dot I equal to 1, 2, 3, 4. You take a linear combination and construct A alpha R and B alpha R equal to 1 and 2, and A alpha R dagger, B alpha R dagger, the linear combinations of Q's. And A algebra will have this plus this on the right hand side, like we had for n equal to 2, and B algebra will have this minus this in 1, and other for R 1 and for R equal to 2, this will have this minus this. So they have to be, this bound will emerge from the same kind of an argument. And now, a representation theory for masses which don't saturate this bound is the same as 1 of the massive multiplet without central charges. But the interesting one is when these bounds get saturated. So we'll do that. BPS saturated states, and that is M is equal to root 2 Z1, and that's root 2 Z2. Central charges are equal, and not only that, they are equal to mass up to some normalization. And then we have these oscillators A and B's. The B's go away, we are left with only A's, and you normalize the A's, normalize the A alpha R to A alpha R hat and A alpha R dagger to A alpha R hat dagger, and they satisfy the algebra A alpha hat R hat S beta anticommutator dagger alpha beta RS A alpha hat R A beta hat S anticommutator 0 A So remember, R takes two values now, so does S, and alpha takes two values, 1 and 2, so does beta. So we have four fermionic oscillators now. And we construct the representation the same way that we have been doing it. It starts with a vacuum state or a ground state. On which A alpha hats are 0, and create the states by applying A hat R alpha daggers on omega. Now, how many states do I expect here? Let me write down that first. How many states? Number of states. I have 4 sets of oscillators for 2 values of R and 2 values of alpha. So I have 4 algebras. And we'll call this a short multiplier. We call it a short multiplier as against massive n equal to 4 multiplied for SUSY without central charges. And that number was 2 to the 2n, and that's how much is that? 2 to the 8, and 2 to the 8 is 256, is that right? It's a long multiple. So now let's tabulate this. N equal to 4 BPS multiplied. How do we start with? We start with the state, number of states, and JZ spin. Vacuum state 1 is only one of them, and give it a JZ value, some JZ, which could be a Bose or Fermi. And apply 1 A alpha dagger R on this. Again, out of these 4 of them alpha 1 and 2 and R1 and 2. Alpha 1 and 2 raise, if you just look at the algebra, raise the JZ spin by half unit, and for alpha, yeah, here, alpha 2 lowers it. So we have two oscillators which lower the JZ spin by half and two that raise. A1, let me write it here. A1 R hat, there is a hat in this all, raises JZ by half, and A2 R dagger lowers JZ by half. So anyway, now first let me say how many states are there, because there are two values here, there are two values here, there are four of them. Two of them will have JZ spin increased by half unit, and two of them will have JZ value decreased by half unit. Now let me apply two of them. A1 hat R dagger, A2 S dagger. This is 1 and 2. R and S. R and S can take values. They cannot take, yes, they can take two values here, two values here. So this is how many states? 4. But this is 1 and 2 down here. One of them will decrease the JZ value, other will increase it, which means will be the same as this. Then let me take A1 dagger, 1 dagger, and A1 hat, 2 dagger on. Both are 1 1. Spinner index is 1 1. Internal space RS is 1 and 2. So this one will increase the JZ spin, this one will also increase the J1. So that is, and there is only one state like that. Now let me take 2 1 dagger, 2 2 dagger. Change this. That's also 1, but that will have JZ minus 1. Because 2 will lower JZ value by half, each one of them. So that is JZ minus 1. So that is one with 2 oscillators. Now I can apply 3 oscillators on the ground, on this ground state. So let me take A1 hat dagger, A1 2 dagger, A2 R dagger. Now these are 3 oscillators. These increase this J spin by half unit. This one will decrease it by half unit. Since R takes values 1 and 2, there are two states here, both with the same JZ value. Then A2 dagger 1, A2 2 dagger, A1 dagger, R. So there are these states now. Again, R takes two values, so there are two of them. 2 and 2 here will decrease the J spin by half unit, and 1 will increase it. Okay? Then the last one, A1 1 dagger, A2 2 dagger, A3 3, sorry, A1 3 dagger, A2, no, error, A1 1 and A2 2, 1 and 2 dagger. So all the four oscillators, A1 1, A1 2, A2 1, A2 2, all the four oscillators, and there is only one state there. And since there are two ones here and two twos here, they will raise and lower by the same amount. JZ spin is 0. This is a general representation of n equal to 4 BPS states. How many of them are there? 1 plus 4 is 5, 5 plus 4 is 9, 10, 11, 11 plus 4 is 15, 16. So 16 states. And 6 bosonic, 6 fermionic. Sorry, 8 bosonic, 8 fermionic. Because if I started with Z to be bosonic integer values, they will keep alternating. If Z is half integer, to be fermion, keep alternating. In particular, let me take a multiplet with starting value, starting spin, starting JZ spin equal to 0. That means the state, vacuum state has JZ 0. So what do I have here? Let me write it here. JZ equal to 0. Here, what do I have? I have half, half, minus half, minus half, 0, 1, minus 1, half, half, minus half, minus half, 0. So I have 3 zeros. I have 1 plus half and 1 minus half. Plus half minus half with 1 0 will make a massive vector. The other zeros, 2 zeros will be scalars. So I had 2 scalars So, two scalars or one complex scalar, and in fact it is a scalar plus a pseudo scalar, one vector, massive vector, which has 3 states, and then fermionic states 1, 2, 3, 4, 5, 6, 7, 8, 8 fermionic states, which combine into 2 Dirac fermions. And you could give it a name, this multiplet. Since it has a, well, not maybe this one, this is not special name, but I'll, so, but it's a short multiplet. I don't want to rub off that, but let me rub off this. Three scalars, are there? Well, 2 scalars. So, some is not working out. Sorry, yeah, I didn't count them. Did I count them right? So, yeah, there are 2 here, sorry. 2 here. There are slow. There are 4 scalars. There should be 5. Is that now? That's 5 is correct, huh? How do I see 5? Oh, there are 4 here, right? I didn't count. 4 plus 5. There are 6 of them.
No, one is for vector.
One goes in the vector, so there are 5 scalars, right? In fact, it's, yeah, you're right. 5 scalars. Correct. That's correct, in fact, 5 scalars. In fact, 2 complex and 1 real. That's correct. In fact, soon I'm going to make some statement. That statement would have gone wrong with this count that I wrote there. And this count is very important for that. All right. So what we have is that n equal to 4 BPS states make a short multiplet of dimension 16. And contrast that, we have already made the contrast this with n equal to 4 massive. But now I want to contrast it with n equal to 4 massless representation. Without central charges. How many did we find there? 2 to the n. for n, and 2 to the n is 2 to the 4, that is this is also a short multiplet. All right. And did we do this exercise, that short multiplet, what does it have? The field content. And if you recall, the field content is, states in this are 6 scalars, real scalars, one vector, but one vector is massless. So it has only 2 plus 4 massless fermions, Majorana fermions. Each has 2, 8, 6 plus 2, 8. So now I think you see the remark I'm going to make. So I wanted 5 plus 1 there. So the spin 0, Jz spin number is same here and there. Jz plus and minus 1 is the same as here and there. And Jz plus halves and minus halves in fermions are same here and in the BPS states in these two. Right? This one has a massive vector field. This one has massless vector field. But how do we give masses to vector fields? We give it through, we start with massless field theories and give vacuum expectation value to some scalar field, the Higgs mechanism. And that's how we generate masses. So for extended means n greater than, so no, let me write it here. Extended, that is n greater than 1 theories, we may start with massless fields or massless multiplet and introduce massless multi-fields or a multiplet containing a vector field and give mass to this vector field by some vacuum expectation value of a scalar. That's how we do it in standard model. That's Higgs mechanism. So this is true for n equal to 4, also n equal to 2. But since we have a certain number of states in massless theory, when you break, you introduce vacuum expectation of a scalar field and introduce Higgs mechanism, you have given masses to some of them or all of them. The process cannot change the number of states. The total number of states have to be same. So we would have a massless theory of n equal to 2 or n equal to 4, and we break it spontaneously through a vacuum expectation value of Higgs and generate a massive multiplet. And such a massive multiplet should have the same number of degrees of freedom as the one massless one had. Because where would other degrees come from? So therefore, such a massive multiplet cannot be a long multiplet, because we started with a short multiplet. Massless theory was a short multiplet. So it again will have to be a massive short multiplet. Therefore, such masses have to be BPS saturated. Clear? Masses so generated have to be Is that clear? You don't have to do anything. Just from the properties of the representation, we get this basic fact. You could, if you write that way, then you would have not have a renormalizable theory, right? So in order to get a renormalizable theory, this is the way we do it. In order to get a renormalizable theory, you start with a massless theory, and then introduce masses through Higgs mechanism. This point is a very important point. Clear? This is for extended supersymmetries, not n equal to 1. Because n equal to 1, I can have, can anybody tell me for n equal to 1, I don't need this? There is no central charges. So this is only for extended. So this is remark number 1. Another remark is that, this argument is more powerful than this, what we have stated. Now, if I write a quantum field theory, n equal to 2 or n equal to 4, extended quantum field theory with massless multiplet containing a vector field, and do the Higgs mechanism, I generate at classical level a representation of the massive BPS massive multiplet which saturates this. Now, if I were to study the quantum nature of this theory, the quantum nature means add quantum fluctuations to it. Quantum fluctuation is not going to change the spectrum of the theory. The number of states is going to be same. So if number of states has to be same, the masses may get renormalized, central charge may get renormalized, but this relation has to be true. So this relation, saturation relation for massive multiplet, massive BPS states, m equal to loop is an exact relation in any order of quantum perturbation. So this property will survive under quantization. Not only perturbative, will survive even non-perturbative quantum features. It's because the number of states cannot change.
No, but if I have bound states in my spectrum.
Your bound states are not elementary states. You can have bound states, they will have their own spectrum.
Yes.
That's different. But elementary states.
No, but if my theory is non-perturbative, then the bounded states.
But they will also form a supermultiplet.
Yeah, but that supermultiplet will not be a BPS.
That supermultiplet would also be a BPS, but doesn't matter. But point is that that supermultiplet will have its own structure. That is not to be counted in terms of the elementary states, right? We're counting the elementary states in both theories. Okay? I'll take 5 more minutes and make a few more general remarks now. Essentially, I'll remind ourselves about some things that we have learned. Oh, one more remark maybe here. There's a sum, before I rub it off, yes. Sometimes you may have heard BPS states break supersymmetry to half. That statement is already here. Because we said the number of states in a BPS supermultiplet is the same as number of states with half the supersymmetry of the massive supersymmetry. So from n equal to 4, n equal to 2 multiplet we saw has the same content as n equal to 1 massive. That is because the B oscillators were trivially 0 on all states. So half the supersymmetries are trivially true. The only other half is there. So BPS states break or reduce to half the number n to 2, n equal to 2 to n equal to 1 and n equal to 4 to n equal to 2. So general remarks. What do we want to do? We want to build up renormalizable field theories which have supersymmetry. So renormalizable field theories with supersymmetry. What does that mean? It means that no spin greater than half in massive theories and no spin greater than 1 in massless theories. Because if massive theories, if you have spin larger than 1, half, which means you have spin 1, massive things, they are not renormalizable. If you introduce mass directly, but if you introduce through Higgs mechanism, they are. And if they are massless, then you can have spin 1, but not spin 3 halves or higher, or spin 2. So now let me start. N equal to 1 we can have a massive representation containing two spin zeros, that's a scalar plus a pseudo scalar, and two states of a Majorana spinner. We constructed this multiplet. And this is the only multiplet we can construct. Any other multiplet that we would have had would have more than spin half. But massless ones are massless. There are two possibilities. One is the same kind, this could be massless, two spins, two spin zero, scalar plus pseudo scalar, and one Majorana. One Majorana fermion, which has two states. So that's the massless version of this one. But in addition, now we can have also a representation with one vector helicity plus minus half, plus minus 1, and one Majorana. Helicity plus minus half. Any other multiplet that we construct of n equal to 1 will have higher spins. So, if you want to write a normalizable field theory with n equal to 1 supersymmetry, you can write only with these three types of multiplets. One massive on its own, other one massless. You can have many copies of these because there will be different representations, but you cannot have any other representation. So, if I want to write standard model as a supersymmetric theory, I will have to construct it, and the standard model will be constructed with massless fields and then do Higgs mechanism together. I will have to construct them only with these representations. There are none else. I can have several copies of them, but this is all. Clear? And now, let's go to n equal to 2. No massive multiplets are possible. If I wanted a normalizable field theory, if I don't want a normalizable theory, I can do it. But massless ones are. Massless multiplets are possible. Can I take 10 minutes today extra? You don't have anything after this? Do you have? 5 minutes, I'll close this then. I don't have to do it, huh? Now, what are the possible massless representations? You start with a ground state with spin 0 and act AI oscillators on E0. I is 1 and 2, and each one of them raises the helicity by half unit, if you remember when we did the representation theory. So this is E, this is so E1 and 2, and then E1, A1, A2 on. So this is 1, 1. No, sorry, this will be plus half, plus 1, because each of these oscillators increase the helicity by 1 unit. Massless representations. And this, we said that it's not CPT self-conjugate. So to this we add E minus half, right? Minus 1. This was one state, these were two states, this was one state. This is one state, two states, and one state. This together made the photon multiple, because it has one vector particle, mass is one vector particle, and two scalars and 4 fermion states. And what is the field content now? Well, field content, we have said it. One complex scalar, one massless vector field, and 2 Majorana fermions. And this is the only one that's possible. Because anything else then that you have will have more than spin 1. There will be helicity minus 3/2 states coming in. We don't want them. So now n equal to 4. No, in fact, there should be n equal to 2, there should be one more. Sorry. N equal to, this is 1. There is one self-conjugate representation, which will come from, E. There is one more, this one. This will increase the helicity. This is 1, 2, 1. For n equal to 2, there are 2 states. But n equal to 4, there is only 1. And have I written it down somewhere? I think we constructed that. Is it still there? Yes, it's there. So no massless, no massive states. No massive multiplet. But massless one, only one. And that is I think that was in, did I give it an exercise? Start with E minus 1 and apply E daggers on this. This is minus half, this is 0. This is the multiplet. One state, 4, because there are 4 oscillators here. This is 6, 4, and 1. And this contains a vector, a massless vector with helicity plus minus 1, 6 scalars, and 4 Majorana fermions. Helicity plus minus half and plus minus half. And 4 of them, so there are 4 of them. 8 plus minus half plus minus half. This is the only multiplet that you can write a renormalizable field theory for n equal to 4. Of course, you can take many copies of this multiplet, and if there are many copies, you can make a non-abelian theory. This would be Maxwell's n equal to 4 Maxwell's theory. So you could make a non-abelian theory, and that would give you this. You can make non-abelian n equal to 4 non-abelian supersymmetric Young means. And it has very nice properties. If some of you already know it, it has. It's perhaps the only 4-dimensional theory that we know is finite. If you calculated beta function for this theory, you will find it 0. I think I'll stop there.